Okay, so we're about on time. So,
I'm so
hi
glad
everyone,
we're
this is
all
our
friends.
second session of the day, our only 8192 level session of the day, and that's Hugo with his debugging without the debugger, investigating SQL Server's internal structures. Over to you, Hugo.
Thank you very much. Welcome everyone to my session. A special word of welcome to Ben Weisman. He will be my moderator today. If you have any questions, type them in the chat of the Zoom or type them in the Slack channel. He will interrupt me, read the question out loud, and I will try to answer them. Before I start on the session, let me introduce myself. My name is Hugo Kornelis. I make SQLServerFast.com. SQLServerFast.com is a website that I created a few years ago because I love execution plans, but I hate the documentation that is available, or rather the lack of documentation that is available for SQL Server for execution plans. So I started creating that documentation myself in the form of the execution plan reference, where I try to document everything about execution plans. A reference is not a good learning resource. So when people ask me, do you also have teaching material available? I started recording the SQL Server execution plan video training. This is an in-depth training on execution plans at a starting level and an advanced level. Some of the videos are available for free. Some require a small amount of money to gain access. That access is then for life. And if you are watching this and you are a fast decision maker, then you can buy access to all my videos with a 10% discount if you use as code the name of this conference, but of course in true geek style, converted to bytes. I also have other content on SQLServerFast.com, like my blog, like some longer articles and resources. I will later upload the slide deck and the demo code to this the GitHub resource of 8KB, but you can already download it now just by going to SQLServerFast.com, then click Other, click Presentations, click Presentation Resources. You will see a list of all my presentations. Just click the one called Debugging Without Debugger, click the download link, and you will have the PowerPoint and the demo code. I do a lot of other stuff as well, but nobody really cares about that. The only thing people really care about is how to contact me. If you have questions that you do not get around to asking now, if I go too fast and you can't even keep up with question asking, or if you watch this video later and you have a question then, mail me or tweet me. I'm always happy to try to reply to questions from the community. So these are my contact details. Use them as appropriate. The main attraction of today will be the window spool operator. The window spool operator is one of many operators you can find in execution plans. And what it does is it stores incoming rows in an internal work table and then uses those stored rows to send that data multiple times to its parent operator. Now, this is a rather generic description that goes for all spool operators. It also goes for table spools, it also goes for index spools, and even in a way for a row count spool. But the window spool is specifically for use with windowing functions. So before we dive into the internals that will be the main attraction of today's session, I will first give a short explanation of what the functionality of the window spool is. That was the wrong screen. I need to be here in the demo screen. So first things first, I have created a special instance of SQL Server for testing purposes, for this specific test, where I have a TempDB with just a single file. That is not a best practice, but it's easier to find stuff in a TempDB of one file than in a TempDB of multiple files. I've created it large enough to make sure it won't auto-grow, to make my environment more stable, small enough to prevent IAM change. It also simplifies my search. I will get back a bit later to this a bit later. And for the demos in this session, 10 megabyte was enough. I also have disabled parallelism by setting the system-wide max DOP to 1, another absolutely not recommended setting in a real production environment, but I've done that to facilitate some of the tricks I'm going to use and make my life a bit easier. So here is a query where I use an aggregate function in combination with the over clause. And this allows for an optional partition by. I don't use partition by here. It requires an order by, and it has a rows between specification that has rows between 10,000 preceding and 3 following. If I execute this, and I will enable the live query statistics, I can talk you through the execution plan while the query is running. Now, what happens, starting with the following the data, we do a clustered index scan on the sales order detail table. And if you look at the details, it helps to click in the right spot. If you look at the details, you will see that the ordered property is set to true. I very deliberately created a query where the order by matches the clustered index of the sales order detail table, because otherwise I also would have had a sort operator in the execution plan, and sort operator can also use tempdb. I want only one thing using tempdb so that I can focus all my research on that, and I know that if I find activity in tempdb, it is the activity I'm looking for. What I'm exactly going to look for will be more clear later, but let's not get ahead of ourselves. The data after being read by the clustered index scan goes through a segment operator. Now the segment operator is here to support the partition by clause that is not here. The reason that there is still a segment here is that internally a partition by clause is always added even if it's not there. So internally this is converted to, it's hard to type when there is a microphone just above your keyboard, partition by an empty list. This is not even valid syntax, but internally it is valid. So we have a partition by an empty list. The entire data set is considered a single partition. And that's why there is a segment operator here, a segment operator that does not have a group by property. You see here, it is listed, but it's empty. So there is no partition by, everything is one single partition. And the implementation of segment is that it will create a column called segment 1008 that is set to 1 on the first row of each partition and 0 on every other row. So in this case, it's 1 on the first row of the entire data set and 0 on all other 120,000 rows. That data is then fed to a sequence project, and this sequence project computes a few values, or rather one value, a value row number 1005, that is computed as the row number. This always resets on a new partition, but because everything is one partition, all data is numbered with rows from 1 to 120,000 and a bit throughout the data set. That data is then used in the compute scalar here. Let's look at the defined values of this friendly friend. Here we have a computation for a top row number 1006, computed as the row number minus, and that's unreadable because of the rectangles, minus 10,000. And we also have a bottom row number, let's do that again, that is computed as the row number plus 3. The current row number minus 10,000 and the current row number plus 3, if you looked at the query, you will realize that minus 10,000 is 10,000 preceding, and the current row number plus 3 is 3 following. So those two computed columns, top row number and bottom row number, specify for each row the first and the last row of the window that the max function is going to look at. Then we have another segment. This segment operator is really not needed because it does the same partitioning as the previous segment column. If I add a partition by here, partition by something, then both segments will use that same partitioning. And we already had a segment column with that same partitioning. So this is basically a useless operator. I am not entirely sure why it's there. It might be because this is simply a standard pattern where the optimizer always creates this pattern of two operators, a window spool and the segments. Or it might be that window spool for some internal reason requires a segment operator as its child and cannot work on a segment column that was computed elsewhere in the execution plan. Either of those explanations is possible. But what we do here is once more compute a segment column that will be 1 for the first row and 0 for everything else. But if I would add a partition by clause to the over clause, then it would be 1 for the first column of each partition. And then we get to the window spool, the operator we are going to talk about today. This window spool actually returns, let's use the output list here, that's slightly more readable. Rather, no, it's not. Let's look here. It returns several columns. It returns the sales order ID, the sales order detail ID, the carrier tracking number. Those are all columns that we want in our final output. So it makes sense that they are there. And then it also returns the row number column that was computed before, the segment column that was computed by the segment operator, and a new column, window count. To compute all that, it uses its input, which comes from the segment. And there you see for part the same columns, sales order ID, detail ID, carrier tracking number, and the row number, and also that segment column. But now also the top row number and the bottom row number that were computed before. And then the data that is returned by the window spool to the stream aggregate goes to a stream aggregate that groups by this window count column that is computed in the window spool, and that then computes sales order ID, sales order detail ID, carrier tracking number, and a new column, expression 1001. Looking at how they are defined, the compute, I said click there. Yes, the compute scalar computes expression 1001 as the max of a carrier tracking number. Well, that makes sense because we have that in our query. All other columns, like sales order ID, are computed using the any aggregate, an aggregate that is only available internally. We cannot use that in our queries, but the execution plan can use it in places like here. You will also perhaps notice that the window spool returns an insane amount of rows, and that is because of how the stream aggregate and the window spool interact with each other. For each row that window spool receives from the segment operator, and that's a total of 120,000, for each of those rows, it will return first the row itself, and then all the rows in that window. So with a window rows between 10,000 preceding and 3 following, when window spool processes the first row, it will return that row and then the first 4 rows. When window spool processes row number 20,000, it will return rows 10,000. It will first return row 20,000, the current row, and then rows 10,000 until 20,003. That's 10,005 rows in total, returned for every row, except for a slightly smaller window at the start and at the end of the partition. And that's why we have such an insane amount of rows and why this query runs so long. It's a total of 1.1 billion rows that are returned from window spool to the stream aggregate. And the stream aggregate returns that 220,000 rows because it aggregates by this window count column that was added in the window spool. So that's the total what window spool does. It stores all the rows that it gets from segment in a work table, and then uses that to, for each row that it receives, output that row enriched with this window count that increases for each row, followed by all the rows in its logical window. And stream aggregate can then aggregate all those rows in its logical window to compute the aggregate, be it a max or a sum or an average or whatever aggregate you specify. So that is the logical function of a window spool. Are there any questions about this?
There are none so far.
Good. Then I'm going to continue because this session is not even about the window spool. This session is about the internals of a window spool. Like I mentioned, window spool stores the data in a work table, like all spools. And if you look online and try to find documentation on how this work table is stored, you will find something. What you will find is if the rows between specification is such that the optimizer can guarantee, based on the query text only, that the number of rows can never exceed 10,000, then it will be in memory. If it might ever be more than 10,000, then it will be on disk. And now you will understand why in my query I said between 10,000 preceding and 3 following, to nudge it just over 10,000, so that in this case it is an on-disk work table. And that's because I wanted to explore the on-disk version. How is this on-disk version stored? That was the question I asked myself. And when I tried to answer it, I ran into a few problems. The first problem is, it is a temporary structure. As soon as the query finishes, it will be released. The query I just ran, it took 7 or 8 minutes, but it has finished now. So some of the structures used in TempDB might still be allocated and still have that data there. Some may already be overwritten. Pointers to that structure are probably all already erased because nothing should point to that structure anymore. It's free space again. So if I start to investigate now, I'm very likely not to find anything, or to find stuff that is being damaged by internal processes in SQL Server, also creating temporary structures and reusing those pages. The investigation can take a lot of time. The first time I started to do this kind of investigation, and the first spool I investigated was actually the table spool, but I had to solve the same problems. It took me several days before I finally had an idea of where to find the data. Query duration is limited. Even a slow query like the one I executed runs for 7 or 8 minutes, and then it's done. So how are we going to fix that? I can start investigating and then rerun the query, but the problem is it's not stable. It's all temporary. It will be somewhere else. So one option that I definitely considered is use the debugger to halt the process. Now, I have never used the debugger. I have sometimes seen people like Bob Ward use the debugger during sessions, and my brain melts when I see them use all those 1 or 2 letter commands and fiddle with hexadecimal data, and I'm simply not smart enough for that. It's too complicated. Yes, it would be a benefit that I can access everything, even internal memory structures, which I don't need today, but it would be a benefit. But I can't handle the complexity. I cannot even use SQL Server commands to help me out. And SQL Server has such nice commands that you will later find will help me out. But if I halt the SQL Server process because the debugger halts it, then my SQL Server commands will not run because the process is halted. And if I unhalt it, then the query also continues to run and I may run out of time. So I didn't want to use the debugger for all those reasons. I can slow my query, make an even slower query. If you know how to tune queries, then you also know how to make them slow. Basically, do everything you should never do. But even a very slow query can finish at one point. And if I am investigating and then my mother calls, then that might take an hour. If I had a query that runs for 1.5 hours, suddenly I only have half an hour left for my investigation. So this is also not a guaranteed safe way. And then I realized I don't have to do anything smart. I can use standard SQL Server functionality. I can create a query that is blocked by another query on another connection. And because it's blocked, it will at one point stop and wait for the lock to be released. But I control when that lock is released. I can keep it up for days if I want to. And that's the method I decided to use. The best part here is it's fully supported. So I'm not even using anything unsupported or undocumented. I'm just using standard SQL Server functionality so far. That will change, but for now, It's all standard functionality. Let's look at the demo to see how I did that. So what I did was basically, and I have it as command here, but run the same query. The reason I have it as command is because I already ran it. It's several minutes. I'm not going to rerun it. I already ran this in demo 1. I have an execution plan and I have the results. And that's what I need. Now, based on the results, I know that there are 4 columns in the result: sales order ID, sales order detail ID, a carrier tracking number, and another carrier tracking number, the max carrier tracking number. What I'm going to do is I'm going to create a table with exactly those 4 columns. And I'll do that in a new window. So I'm going to create a table with those 4 columns. And because I know in the data that the sales order ID, detail ID combination is unique, because the input data has that as a unique data, and I'm not adding or deleting any rows, this is also the primary key for this. So this is a table where I will store the results of the query. So basically, I'm going to execute this query again, but now with an into clause to store the data in this table. However, I'm also going to insert a single row in that table. And you see here that the first 2 values are populated. Those are the primary key values. The rest is irrelevant. By inserting this row, I make sure that at one point, SQL Server cannot insert a row. Which row? I deliberately select a specific row. Let's see, I need to go a bit further down. I deliberately took row 10,100. So these are the values, 46,359 and 10,100. And those are the exact values I have here. So by the time SQL Server wants to insert this row, which is the 10,100th row, and I deliberately took a row slightly over 10,000 to make sure that we have a full window here. By that time, SQL Server will block, because after running this, and you see that the rollback is commented out. So after running this is blocked. Now, one other thing I need to do before running this, apart from making sure that I'm in the right database, is check the execution plan. Sometimes inserting affects the execution plan, because sometimes SQL Server wants to optimize for the insert and a different order is called for. So I did a double check where I looked at the execution plan. I looked at all the properties of all operators to make sure that exactly nothing was changed, except for the addition of this clustered index insert. In this case, I was satisfied that I do indeed have the same execution plan. If I have the exact same execution plan with the exact same properties, then even though I don't see the rows produced, they are inserted in a row in a table, they will be produced in the same table. So the 10,100th row will be this row. Let's execute this without highlighting half a statement. Let's execute this. Let's stop it again, because I forgot to include the actual execution, the live query statistics. Let's execute this. And now the query statistics are running again, but now this query should freeze rather fast. Like I said, after 10,100 rows, and that should only take a few more seconds. So I'm buying a bit of time by saying some nonsense, but soon we shall be there. Now you see that the timers are still running, but the row counters have stopped. Interesting to see, this segment has actually returned 10,105 rows, because the window spool needs to read ahead a bit to also produce the 3 following rows. The stream aggregate has returned 10,100 rows, but the clustered index insert has only processed 10,099. It is trying to insert row 10,100, but it has to wait until the lock is released. And I decide how long that lasts. Well, I have had my demo, so now I can roll back this transaction. And as soon as I do that, this execution will continue. And if I don't stop it, it will run for 7 more minutes. But I don't need to do that again, so I'm going to stop it. So this is the method I can use to completely block this query from stopping, and the work table that the Windows Spool uses will remain in TempDB all that time, and it will not change. It will be completely stable. So there will also be no page splits, nothing. It will simply not change at all. And that's exactly what allows me to spend as much time as I need to try to find the data I'm looking for. That was one problem solved. Now I need to find the objects. So of course, I simply type select star from the tempdb.dbo. Wait, what's the name of the object? Okay, let's go back to the demo. I already ran this demo and I did it with statistics.io on, so that we see here that there is indeed a work table with a lot of reads. So this is the work table used by the Windows Spool. But trust me, if you type select star from tempdb.dbo.worktable, you will not get your data. This is a generic name. It is not the name of the specific table. It's not that easy. It's never easy. So try something else.
Can I ask a question before you
Yes,
move on?
of course. Please do.
How do you, well, technically it's Mark's question, but how do you ensure that the logging is done at the row level and not the page level?
By default, SQL Server always logs at the row level, never at the page level. It can escalate to the object level if the number of logs is too high. And I don't know the threshold by head, but in this case, it's just a single log. So it will always be a row level unless I myself have explicitly overridden the default to use page level logging. And frankly, in my entire career, I have never had a reason to do that. More questions?
Not for now.
Okay. So the next thing I wanted to do was query sys indexes. Or if that doesn't work, the deprecated sys.sys indexes, which has some more internals. And to facilitate that, a simple way to query those tables they return a lot of data and it's hard to see what it belongs to. So what I decided to do was run the query twice. Once before I create a work table and once after I create the work table, then compare the results. There should be an extra row, right? So let's do that in my demo. I still need this. I don't need this anymore. I'm going to close windows I don't need anymore. Otherwise, I'm going to confuse myself. So I have this query that returns data from sys indexes and from sys indexes. I'm going to copy the text to a new window. And now I have the same query twice. Let's execute one of them. So this is the query executed before anything started. There is no work table allocated now. Now I'm going to set up my blocking table again. That's why I also have a drop table if exists, so I can rerun this script. And I'm going to execute this query again. At this point, there should be a work table. So here I have a list of everything in sys indexes and sys.sys indexes before the query started. Now the query has started and I'm going to execute the same query, but I do it in a different window so that I can easily compare the results. So I can do things like click in the first result, Control Tab, click there, Control Tab, do a page down in both. And that's a way I do need to make sure to do the same page down, that I can compare the data. But I can also just look at the total number of rows for both queries combined. And in the first window, that's 386. Cool. In the second window, that was before I started the query, I'm still in this window. I need to be outside of that window. It's also 386. So I got the exact same number of rows in both cases. So apparently, whatever is stored in sys indexes or sys.sys indexes for this work table is filtered out when we query it. Okay, but I'm a smart person and I know execution plan, so I'm going to look at the internals. And I forgot to enable the execution plan when I ran this query, but I did have it here. So I cannot compare the two, but when I did this, I had the execution plan enabled on both and I could compare that data as well. So what I did was, for instance, for the first query, select star from sys.indexes, and I did the same for the second query, go through this execution plan to see the actual internal tables that data is being pulled from. And for instance, and I noticed that main data comes from sys IDX stats. And there is a filter here, a predicate, that uses some bit mangling on a status column. Aha, so this is perhaps where internal stuff is filtered out. So at this point, you can do various things. One thing is to click here, go to the full properties, and look at the table cardinality. This is a bit misleading because it's the table cardinality when the plan is compiled. And this plan was, of course, reused, but perhaps a row was added. So I could have forced a recompile, but I can also try to investigate the actual data stored in sys IDX stats. Let's return to the slides to see how that can be done. So the answer is already on the screen. The object is not stored there, but how did I find out? Well, one thing I did is what I mentioned, compare the number of rows in all operators of the execution plan plus runtime statistics on sys indexes and sys.sys indexes. I looked at but then I also wondered, perhaps the data is there, but it's filtered out, like I mentioned. But then you can look at the actual data in the system table. There are two ways to do that. One is to have a separate dedicated administrator connection to the database. On a DEC connection, you can actually read the internal system tables. Another method you can use is to use dbcc page to actually inspect the contents in the system tables. Then you first have to figure out on what pages they are stored, and then you can inspect those pages. That is the method I actually used. And it turned out that there was simply nothing stored there. The internal object for a window spool is not stored not even in the internal system tables for indexes, because SQL Server doesn't need it there. And then why would it store it there? It can just keep it in memory for the query that is using that window spool, and it doesn't need it anywhere else. So at that point, I had spent lots of hours and I felt like I was running into a brick wall until I realized, even if SQL Server doesn't need any pointers to this temporary object outside of its current connection and can just leave it in memory, it still needs to protect those pages. You don't want another process thinking this is a free page, I can write something there. So objects like the page free space, yeah, that's the demo I just did, sorry. Objects like page free space should still be maintained because the page is not free anymore when it's used for this work table. So that was my next approach, to go to the PFS page and use that to detect differences. Find a page that was not allocated before you ran the query that is allocated now, and that is very likely to be a page that belongs to this spool, to the work table for this spool. And then I struggled once more after I found the first page to find the next pages. I can use the next page and previous page pointers to find pages on the same level, but pages on a different level are not easy to find, until I came across a post somewhere that used DMOS buffer descriptors to find pages based on an allocation unit. I had the allocation unit available in the page, and it turned out that this system view works, even for internal tables. So that saved me a lot of time to quickly find all pages. Let's use this in a demo and then use dbcc page on all the pages of this work table to inspect the contents. Let's see, you need this query anymore. I don't need this query anymore. Let's stop this and roll back this transaction. Now, one thing I'm going to do before I do the last step is restart the instance. The reason I do that is because I noticed when I first started trying to do this, I didn't always find what I was looking for, and I figured out after some trial and error that specifically in TempDB as a kind of optimization, when pages are allocated and then they are not used anymore, they are not automatically given back to the system, at least not immediately. TempDB keeps them allocated because allocation for TempDB is often up and down again. So it saves overhead. If you don't return those pages immediately, you then have to request them again. It keeps a bunch of pages that are technically not used. It keeps them allocated for itself because it knows I will use them soon enough again. So now I have completely restarted the instance, and TempDB hasn't had any request yet, so there is nothing allocated yet. And now I'm going to use this part of the code and copy that to a new window. And the DBCC page statement is not officially documented as far as I know, or maybe it is now, I'm not even sure, but Paul Randall has officially blogged about it when he still worked for Microsoft, and I consider that official enough. It's still something you should not use on production systems unless something very weird happens, but this is a specific test instance where I can do this kind of stuff. And here is the huge benefit of having a small TempDB with only one file. If I had 8 files, as I normally have because I have 8 cores, then I would have had to check 8 different PFS pages. If I had a huge TempDB, I also would have had to check multiple PFS pages, because at that point they become a chain, because they each only address have a limited amount of data they can describe, and then if your file is larger, you get a secondary PFS page. But now I only have one single PFS page for the entire TempDB, and I know that everything that I want to check is on that single page. So I execute this query, and what you see in the results is an interpreted list. It's interpreted because I use the style parameter 3 on DBCP page, which means it gives me interpreted data. And the most useful style, in my opinion, it's an interpreted list of page 16 until page 17 are allocated 100% full. Page 110 is not allocated and 0% full, or is allocated. Page 160 is not allocated, and so on and so on. So all that data is here. This is the DBCC page result as it is before I did anything on a just restarted DBC TempDB. Now I'm going to set up the block again. And I'm going to run this. And in this case, I'm going to wait for a bit, because at this point, stuff is moving and happening in TempDB. It's adding rows, maybe even deleting rows. It's doing all kinds of things. And I don't want to try to find anything when the parts are still moving. So it's just a few seconds more, and then everything should be stable. Nothing is happening anymore, because the entire execution plan is waiting until that locked row is released. And now I need to make sure that I don't confuse the windows. This is the window with the before data. Now I'm going to execute the same code in this window with the after data. And at this point, I'm going to make heavy use of Control-Tab to compare the results. Now, the beginning is not very interesting. I'm going to go to the interpreted data, and I'm going to Control-Tab and check whether the data is the same or not. So this takes some effort to make sure you don't overlook a difference. And there is no difference here. This can take a while because I have to go through the entire list and not overlook any difference. And the location is not always the same. Often it's at page 91 or 93, but that was not the case today. Eventually, we should run into something. There we have a difference. Finally, you see a difference here. Before I did anything, page 1384 was allocated, but 385 to 391 are all not allocated. But now that the spool is running, page 384 to 412 are all allocated. And there's more difference below that. So the first difference I see is page 385, which was not allocated here, but is allocated now. It's in this range. So page 385 is probably a page that is used by the spool. Okay, let's look at it, 385. Now, in this case, I'm going to use dump style 1 because that is a safe way to always get output, even if the page is hard to read, because at this point, I'm only interested in the header. So I'm looking at the header, and what I see is a negative object ID. And during my investigation, I also noticed that if you are looking at internal temporary objects, they have negative object IDs. That's also why you can't find anything in system tables, because in the system tables, only positive object IDs appear. However, they also have a normal allocation unit ID. And that is a value I can use. So I'm going to Control-C this, copy it, paste the value here. And now I'm going to use this query to check the DMOS buffer descriptors for this allocation unit. And there we get a list of all pages that are allocated to this allocation unit with a description. And if I scroll down this list, you see lots and lots of pages that have page type data page. You also see one index page at a page level of 0 and an IAM page. If I had waited like 6 or 7 minutes until the and make sure that the window spool would block at the very end after 100,000 rows, and I did that as an experiment when I prepared this session, then you will see multiple index pages, one at page level 0 and multiple at page level 1. So the reason that that happens is this structure is completely identical to the structure of any B tree as stored on disk. An IAM page to track where everything is stored, an index page or multiple index pages to implement the structure of the B tree, and the data pages for the actual data on the root level of the index. This is a B tree. And we now know that the index page is page 385 and the data pages are 384, 386, etc. And we can look at any of those pages to get more information. So let's pop in the number of the index page first. And because there's only a single index page, this is the root page. And I have, in this case, dump style 1. Now, dump style 1 is not very user-friendly. Dump style 3 is much more user-friendly, but unfortunately, when I try it with dump style 3, I get a nice description of the page header and then an error message. DBCC page presents the data in a user-friendly view by using data in sys.indexes and sys.tables and sys.columns. I don't know what the exact names of all those tables are, to understand the structure of the table. But this index is not described in all those objects. So even DBCC page cannot decode this data because it doesn't have access to the metadata. The metadata is only available to the process that runs the window spool, not to this DBCC page. And that's why I used dump style 1, which is less user-friendly, but at least it outputs the data. Now you see the same page header, but then below that, you will see that here is the data for the first row. Slot 0, offset so much. This is the length. Dump style is byte. That's this one here that says dump style byte. Just give me the bytes. And here is the actual data that is stored. I will return soon to the slides where I explain how this can all be deciphered. But this is the first row on the root page of the index. This is the second row on the root page of the index, slightly more bytes. slightly longer data than the row after that. And it continues like that. There's lots of rows here. I'm not going to show them all. Now, one thing I do need to do now, and I need to bring up my calculator for that and make sure to set it to the programmer function. I'll bring it back soon. But one thing I need to do, and I will repeat it on the slide, is that I have to look at the last 6 byte pairs for this row. So that's 3 and another 3. Those 6 bytes are 2 values. This is the file number. And we need to reverse the notation. So you read it as 0, 0, 0, 1. File number 1. Well, we only have 1 file, so that makes sense. The other value, those 4 bytes, are a page number. Once more, reversed reading, 0, 0, 0, 0, 0, 1, 8, 0. 1, that's the wrong window, 180. So we have hexadecimal 180. That's decimal 384. Hey, we saw the page 384 in the results of the previous query. Remember, when we ran this query, we saw that page 384 is allocated. It's a data page. And now we see that the first row on the root level page points to 384. So indeed, 384 does also belong to this object. And again, dump style 3 is not supported. In this case, you don't get an error. You simply get no results at all, which is very misleading. But dump style 1, again, works perfectly. And if I check page 384, you will see that it is indeed allocated to the same allocation unit, the same object ID. And here, and this is the first time I actually almost shouted my happiness. My wife was asleep on the couch, so I didn't actually shout it, but I was so happy when I saw this because I saw 4911-403C-98. Why does this make me so happy? Because in the results of the original query, if I go back to the first row, the carrier tracking number is 4911-493C-98. This data here is the carrier tracking of the first row, of several of the, there were multiple rows at first with that number, but this is the carrier tracking of one of the first rows. So this was an immediate visual confirmation that I actually had found data that is stored in the work file, in the work table. Sorry, it's not a work file. So now it was time to start deciphering this data, and how I did that will be shown on the PowerPoint because that's easier to highlight everything.
Can I interrupt for another question?
Oh, great.
And
yes.
Of course, again, it's not my question. So I hope I'm saying that right. Kai Mikhail, they're wondering, I wonder if it is possible to analyze problems that one would normally analyze with a debugger, like stack traces and memory dumps, using this method as well. Probably not due to the fact that all the data you need is no longer in RAM and you cannot use that trick to block the process, right?
That would be one issue. You would need to know exactly when the problem occurs and stop it there. But if you stop it just before the stack dump, then you're too early. If you stop it just after the stack dump, you're too late because you just had a stack dump. Also, most of that data comes from memory and not from disk. This method cannot be used to investigate in memory data. I can use it to investigate on disk data because I can use DBCC page to analyze the data that is on disk. Even if it's not actually on disk, if the data is still in the buffer pool, DBCC page will either track it from the buffer pool or from disk, but it will always give me the data and I don't even have to figure out where it is. But if I wanted to investigate the in-memory version of the work table of a Windows spool, then this method would be useless because there are no SQL Server commands that allow me to, at least none that I know, that allow me to inspect internal memory structures. I hope that answers the question.
Thank you.
So figuring out the structure, an important part when we try to understand how all the data is exactly stored is knowing what you should expect. You probably remember that I just said I was very happy when I realized this data is exactly one of the carrier tracking numbers. This is data I have seen in the result set, so I have found the correct data. That was a confirmation of my expectation that I should at one point see a carrier tracking number somewhere. And I did. So that expectation was confirmed. But now I'm going to look at the complete data that we expect. And to do that, I'm going to first return to the relevant part of the execution plan. If you look at the segment operator and look at its output list, you will see that it returns a total of 7 columns. I already talked through that at the start when I described the operator. Sales order ID, sales order detail ID, carrier tracking number, the row number, top row number, and bottom row number, and the segment column that the segment operator produces. The window spool also has its output list where it returns sales order ID, sales order detail ID, carrier tracking number, the row number, a new column window count, and once more the segment column. Now, if you see that the first 4 columns are exactly the same from the segment to the window spool and from the window spool to the stream aggregate, then it makes sense to expect that those columns will be stored in the window spool. In the work table of the window spool. Because otherwise, where else would window spool take it from if it has so many rows and it even needs to read ahead because there are rows after the current row that are also in the window. So that makes sense that they are stored in the work table. The segment 1009 column makes the same kind of sense, although I can imagine that you would not store it and simply use it because this is actually a column that's actually used for internal processing in the window spool. So it should be in memory at all times and it doesn't technically need to be stored, but I might expect it there anyway. Then we have the top row number and the bottom row number, and they should definitely be in the window spool because if the window spool is working on the row with current row number 20,000, it needs to find that row 20,000 in the window spool because its read ahead might already be on row 20,004, but it still needs to read back row 20,000 from the work table to realize, oh, I need to return rows 10,000 until 20,003 for the current window. And the window count makes no sense to be stored in the work table because that is computed as the data is returned. So actually, I just expect all the columns that segment returns to window spool with a small question mark for the segment column. But that's the data I expect to find in the work table. With that knowledge, it becomes easier, less hard is maybe a better word, to decode the data on disk. Now, one thing I definitely used as well is this book. It's a very old book. It's called Inside Microsoft SQL Server 2005. Yes, 2005 by Karen Delaney. There are later editions. They are probably just as good. One part of that book describes the structure of rows as they are stored on disk. And every time I need to decode DBCC page input, I always go back to that book. Yes, it's insanely old. It's an almost 20 years old version of SQL Server, but the structure of how data is stored on disk has not, as far as I know, changed at all. There are added additional new structures. You will not find anything about column store indexes in that book, of course, because they didn't exist yet. But for traditional indexes and tables, the data in that book, the description in that book is still applicable. So I just use it. Now, because this is a B tree, we
Quick
have
question on reading pages.
Yes.
So Ivor is wondering, does DBCC page read directly from disk, or does it first ask the storage engine to bring it to memory and then read it from there?
As far as I know, but I'm not 100% sure, it goes through the storage engine. So it asks the storage engine for the page. The storage engine will check whether the page is in the buffer pool already. And if not, it will fetch the page into the buffer pool and then read it. So it will use the buffer pool. And I know that with 98% certainty, but not 100%.
That's close.
The 98 is an estimate. Anyway, we have an index page. We have index pages. In my case, just one index page, and we have data pages. Let's first look at the data on an index page. So index rows have a specific structure, and here is a screenshot, and it will not be exactly the same as what you just saw, because I created this screenshot when I ran this demo another time, and at that point, pages were allocated at a different place in TempDB, and an index page points to pages. So every pointer to a page will be to a different value here because it's to a different page. But the structure, the basics of how to read it is the same. So the first row starts with the byte 06. And the first byte of an index page is a status byte. And Kalen Delaney has described all the bits that are in that byte and what they mean. 06 means it's an index row and there is no null bitmap. No null bitmap means that there are no columns that might be null. All columns are nullable, are not nullable. So there is no need for a null bitmap. That is the first thing to look at. Part of this is even with dump style 1 interpreted by DBCC page. You see here it says index record and it says nothing here. But if you look at the next row, you will see that there it says null bitmap there. So this implies no null bitmap. Like I said, it's an index record, no null bitmap. Then I went to the far right because I know those 2 bytes are the pointer to the page where the first page of the next index level is stored, page 1, file 1. Well, there is just one file, so we expected that. And this is the part what we already did. And then we also have the 4 bytes that point to the page. So this is a pointer to either index level 1 page, or if there is no index level 1, to a data page. In our case, it was a data page. And then we have a bunch of data there that confused me at first until I realized that on the first index entry in any index, the data that is stored in the first field is not used. And if it's not used, then why even bother initializing it? So it's just whatever bytes happened to be on that location in memory or on disk when this data was created. And it's never looked at. It's meaningless content. I don't need to interpret it. The second row had a slightly different index status byte. It says this is an index row with a null bitmap. And again, we found the down page and the down page pointer, file number 1, page 282 in this case, in its standard location. And now this data is not useless anymore. Once more, you need to read it byte-wise right to left. So this is a bunch of zeros and then 7-1, which is the hexadecimal equivalent of 113. That means that the clustered index key, a big int value 113, is the first entry on the page, on page 282. And that is the index structure we expect. To the right of that, you see that there is a number of columns 1. Well, that's the column we just looked at. Why wasn't this there on the first byte? Because there were no columns there. The second row, there is one column, so it's stored here. There's one column, and that one column means that we have a single byte null bitmap, and it's set to 0 because there is no null value. The value is actually 113. And we can look at slot 2, the third row on the index page, for a similar data where it says the value, the first value on page 283 is 225 decimal, 0 hexadecimal E1. And all the other slots, all the other rows on that index page were a similar structure with a higher index key and a different page number. So that completely confirms my expectation that this is a normal B tree. Now we're going to look at the data. And this is where we expect those columns that I highlighted on one of the previous slides. And here is the screenshot. And this should be the same whenever you screenshot it, because this is all data. There are no locations in TempDB here. This is all user data that has been read from the sales order details table. Some columns were added, row number, the first and last row number, and then was stored here. So this should always be the same. But it's a bunch of data and it's not easy to completely understand this. So let's step through this step by step. For a data record, there are 2 bytes with status information. And the data, when they are 0030, as here, remember you read it right to left, byte reversed, then this means that it's a data row, it does have a null bitmap, and it does have at least 1 or more variable length columns. So we do have a null bitmap, we do have variable length columns, and it's a data row, or also a primary record. And once more, DBC page also tells you that primary record is a data page, there is a null bitmap, there are variable length columns. But I was able to confirm it in my Calendar book, which always makes me happy. Now, when you know that it's a data that there is a null bitmap, then the next 2 bytes specify the location where you find the number of columns. The end of fixed data is also called, because the structure is we first store all the fixed length data, then 2 bytes with the number of columns, and then the null bitmap, and then the variable length information. So it stores the position where the number of columns is stored, the end of the fixed length data. That's 0025 hexadecimal or 37 decimal. So I count which byte that is, and these 2 bytes is the number of columns. So we have 8 columns total. There were 7 in my expectation, with, well, 1 had a question mark, the segment column had a question mark, but in reality there are 8 columns. A tiny surprise. 8 columns means that we still need only 1 byte for the null bitmap. So 1 byte, if there had been 9 columns, it would have been 10. This would have been 2 bytes. Now it's just 1. And it's all zeros, so nothing is null in this case. All data is there. There are no nulls. And then the next 2 bytes is the number of variable length columns. That's just 2. So we have 8 columns total, 2 varying length, 6 fixed length. And then we have 2 pointers to the end of each variable length column. So this is a pointer to just after the first variable length column. You could also say to the start of the second varying length column. And this is a pointer to just after the second varying length column, or to the start of the next row. 002E, the end of the first variable.
Question.
Yes.
Is it possible to use a select statement to directly select from the work table?
No, not as far as I know. Like I said at the start, the first thing I tried was select star from tempdb.dbo. And then I didn't know what to type, because this temporary structure is not stored anywhere in any system table. It doesn't have a name. And in a select statement, you need to provide a table name.
That usually helps.
I think that answers the question. So, like I said, I was looking at 002E right here. And that is the end of the first length column. 002E, I counted it, and that was, wait, just after the second length. So this first varying length column has 0 length data in at least this row. That makes it hard to reverse engineer what's stored there, because nothing is stored there. It's a 0 length string or a 0 length varying data. It doesn't even need to be a string. Most varying length data is strings, but it doesn't have to be strings. Keep that in mind. The second value, 0046, is the end of the row, and the data there, it's easy to understand if you look at the ASCII translation to the right. That's the n varchar representation. That's why you have 2 bytes for each character of the carrier tracking number. So we found the carrier tracking number. That's the second varying length column. And we found the first varying length column that we don't understand yet. Maybe we'll figure that out later. But let's first look at the fixed length data. Starting at the start of the fixed length data, I see something that's easy. I see 0, 1, and then a bunch of zeros. I remember byte reverse. That's a whole bunch of zeros and a 1 at the end. That's a representation of the value 1. Given the number of bytes, it's a big int. It's a big int value 1. That has to be this row number column. Row number and then 1000 something. I just call it row number for ease. This is the first row in the work table. It's row number 1. If you look down, the second row in the work table has row number 2, and so on and so on. That was easy. The second part, I actually cheated, because what I did was I typed in the number 43659 in my calculator. I said, what is the hexadecimal version of that? That's 0xAA8B. Okay, I'm looking for 8BAA because I know SQL Server reverses the bytes. 8BAA, hey, that's there. With a bunch of zeros because it's an integer, not a small integer. So it's 4 bytes. 8 bytes, I mean. And those 8 bytes are there. So this has to be the sales order ID, because I knew that I expected value 43,659 from my data that I still had open in my first result set. Remember, in this window, 43,659. That's the number I was looking for. I also expected the sales order detail ID as an integer of the value 1. So that's once more a bunch of zeros ending in a 1, but now an integer, so just 16 bytes. 8 bytes. I keep confusing myself. And that's, of course, there. So that were 3 easy to identify columns that I had down quite quickly. And then I looked at the start of the next line and says 05F1D8, and I scratched my head and I couldn't make heads or tails out of it. So I was a bit stuck. And then I decided, you know what, I'm going to approach this problem from the end and narrow it down by approaching it from the 2 ends until I'm in the middle. So I started at the end of the fixed length data, just before the 0800, that was the number of columns. And there I saw once more 16 bytes, a big int with the number 4. That's a row number plus 3. We saw in the compute scalar that the bottom row number is computed as row number plus 3. Well, this is exactly that value. And once I realized that, I saw that just to the left of this, so the fifth fixed length column, starts with a bunch of Fs. That's a negative number. That's how SQL Server stores negative numbers in reverse binary notation. So those 16 bytes, if you reverse the byte pairs again, you get 0xFFFFFFD8F1, and my calculator told me that's minus 9,999. 1 minus 10,000. Once more, exactly what we expect for, in this case, the top row number. And now I know that the 4th fixed length column isn't 05F1D8. I was confusing myself. The 4th fixed length column is just 05. And on the 2nd row, it is FE. So it's a single byte, but I still don't understand the data. I've made a lot of progress, but I'm not 100% there yet. So let's focus more on the single byte. And I kept trying things, changing things, rerunning things, breaking my head. At one point, it was time to go to bed, and I stopped my SQL Server. I closed my laptop. The next day, I started again. And then I noticed that there was different data in that 4th byte. And that should not happen, because it's the same data that we're storing. So how come the DBCC page suddenly returns different data? And when I ran it multiple times, sometimes it was the same, sometimes it changed. But one thing never changed. The first row in the work table always has an odd number there. And all other rows, okay, granted, I didn't check all 10,000 rows, but 10,100 rows, but I checked a fair amount of them. All other rows have an even number. And that's when it started to dawn on me. I had this question mark on the segment column. The segment column is a single bit. It's not a byte. So that's my theory, that 7 of the 8 bits in that byte are unused, and hence they are just left as is. They are not initialized, and that's what explains why they sometimes have different values when rerunning the query, because it's on a different page. They had different data there, and it was not initialized. But the 8th bit is initialized, and that's why the first number is always odd and the rest is always even, because that's where segment 1009 is stored as a single bit, and the other 7 bits unused. Now we only have 1 column left, and the reason I was able to figure out this column is because I saw an analogy with the table spool and the index spool that I had investigated earlier. Based on the index structure, I already knew this is a B tree. It's an index that is built on the row number column. But based on the analogy with the table spool and index spool structures, I realized SQL Server has declared this internally as a non-unique clustered index. And what does SQL Server do with a non-unique clustered index? I forgot to tell you this, but I looked at a bunch of rows and it was zero ranked on all rows. I couldn't find a single row where it had data. So my theory, because it is a non-unique clustered index, is that SQL Server has a uniqueifier column. There's always a uniqueifier column in every non-unique clustered index that is used to make duplicate entries unique. So the uniqueifier column is always empty for the first row for any value. And then if there are more rows with the same values, then the uniqueifier column gets used and is populated with a 4-byte ascending integer. Now, in this case, the clustered index is on the row number. The row number is generated internally by an operator that never generates duplicates. So there will never be duplicates. But SQL Server still stores it as a non-unique clustered index, which means it always accounts for this uniqueifier column, but it never has to store data there because there are no actual duplicates. And that concluded the last problem, reading and interpreting the data. I had managed to decode, to find all the pages, to decode the index page, to decode the data pages. And my conclusions were, if a window spool creates a work table on disk, then it uses the structure of a clustered index. That clustered index is built on the row number column that is generated elsewhere in the plan and is provided to the window spool by its child operator. It's declared as non-unique, even though there will never be duplicates. That's simply how Microsoft coded it. Don't ask me why. And all the columns that are in the input, even the segment that technically didn't need to be stored, are stored in the work table. So those were all the conclusions I found after using almost completely documented, DBC pages partly documented, but otherwise completely documented SQL Server statements and not using a debugger to debug the internal structures of SQL Server and find out stuff that nobody needs to know and that Microsoft never intended for us to find out. If you try hard enough and know your way around the system, you can sometimes uncover information that you don't need. That concludes my talk. Ben, are there any questions at this time?
I have one question. What is happening? You're finishing 3 minutes early?
Yeah, it's amazing, isn't it?
However, we may reconsider scheduling you in the last session for our conferences. However, there are actually questions.
Good. Then I'm going to use those 3 minutes.
Yes, please. How can you find this temporary structure if you have more spool operators or more work tables in your query?
That's exactly why I created the query that followed the order of the clustered index so that there wouldn't be a sort operator. Because if you have a sort operator, then it might spill to tempdb, and that also creates structures. And I'm not sure if the structure is created even without a spill just to have it there, or whether it's only created when it's needed. I didn't want to risk it. I just didn't want to have a sort at all. If you have multiple spools or multiple other operators that use those structures, then you can still use this technique, but you will have a lot of extra work because you find a page that is allocated to your query because it has just been allocated and cannot be allocated to anything else, but you don't even know what structure it belongs to. So you might be looking at the wrong page. And there is no easy way other than figuring out the data and then saying, oh, this is obviously the data for the second window spool. I was looking at the first window spool. But there's no reason to ever do this in practice, except when you want to document the structure of a window spool. And that has already been done So if you want to know the structure of the Index Spool, just go to the execution plan reference. I have described the conclusions there. So the short answer is don't do that.
What made you sure that you would even find the work table on disk in TempDB? What if it was just a memory structure?
I knew it was not a memory structure because that is actually documented. And I tend to trust Microsoft's documentation if they are so specific that they say if it's more than 10, if it can be more than 10,000 rows, then it is a structure in on disk structure. It's also very noticeable from the performance difference. And you have, of course, also as another confirmation, this row that also confirms that there was actually access to a work table. So I had several confirmations that there was indeed a work table. Did that make me sure I would find it? No. I wanted to find it, but I wasn't sure I would succeed. But I did give it my best, and I'm very happy that I did eventually succeed.
I was going to say, at least you were sure there was something to find.
Yes, I knew there had to be something in TempDB. That was absolutely clear.
There had to be something in TempDB. That's a great title for memoirs, I guess. Camila is still typing from what I can see. Also, I highly recommend you go back to Slack after the session just to read some of the first feedback there. People are complaining that their brains are not melted, but people are also pretty happy and excited and impressed about what they've learned today.
My goal with even with a level 8K session is never to melt brains. My goal is to present brain melting material in a way that does not melt brains. I'm glad I succeeded.
That's a distinction without a difference. I'm just throwing that out there. That's the same thing. They're the same. I was going
to let it slide, but okay.
I disagree with that. You can make it your goal to melt brains by describing stuff in ways that are deliberately hard to understand. And you will melt brains, but you will not help people. I try to do the reverse. Okay.
I appreciate your content, Hugo. That's not a slam.
Thank you. By the way,
I still recommend you go back to Slack, but I want to read one comment to you from Frank Gill, who just said this is the best session he has ever seen. Thank you so much. So I thought you should know that.
I don't have a hat on but I'm tipping my hat.
I actually got 2 more questions for you, and I've gotten permission to go 3 minutes over. So let's use that for these 2 questions.
By the way, I have advanced the slides to where my contact information is repeated. So any questions that I don't get around to now, just mail them and I will take my time for you later.
Perfect. Thank you. So what does scan count 1, 2, 3 in the statistics output mean? Does that mean SQL Server scanned the table that number of times?
Yes. Not necessarily the whole table, but it did a whole or partial scan. And in this case, I assume it's a partial scan. A partial scan means it does an index seek to the start of a range and then scans until the end of the range. Which of course makes sense because we need to return rows 20,000 until 30,005. So it uses the index structure to go to row 20,000 and then scans until it has hit row 30,005.
So question from Camilla, just to clarify, with a smaller set, so less than 10,000 rows, the work file would still be present but not on disk?
If the data happens to be less than 10,000 rows, it would be on disk. It might be in the buffer pool and not actually hit the physical disk, depending on whether there's a checkpoint or not. There's a session later about checkpoints, so I'm not going to explain them further. The table will only be in memory when, based on the text in the over clause, independent of the actual number of rows in the table, SQL Server can guarantee it will never be more than 10,000 rows. So even if there's just 2 rows in the table, if I type between 10,000 preceding and 3 following, SQL Server looks at the query and says, oh, this table might one day grow. The execution plan might get reused. I'm going to use a disk-based work table. But if I type between 5 preceding and 8 following, that's a range of total 14 rows that will go in memory and not go on disk.
Cool. And with that, we are at time. Thank you so much. It was my pleasure and honor to be moderating for you today. Thank you everyone for your great questions. And I think Mr. Matt Gordon will be taking over the moderating spot up next.
Yes, thank you so much, Hugo. That was absolutely fantastic. We get some fantastic feedback in the Slack channel as well. So well done, and thank you so much for presenting.
My pleasure.
I was going to say, Hugo, that was an amazing session. And anybody who references Kaylin Delaney's internals book, which is one of my favorites, she's my spirit animal. I love it.
You're welcome. I'm also a huge fan of her.
Okay, can I grab the screen now, Hugo?
Yeah, I'm trying to figure out where the stop sharing button is, because all
just insult Mark, he will kick you out of the meeting.
Now.
Isn't it at the very bottom?
It was at the bottom of my screen, but that screen disappeared when I started sharing.
Oh.
I can turn it off.
Oh wait, it should be here.
It'll be over in the little box. Yeah.
Now my sharing is paused, but not stopped. That should be enough.
Perfect.
Yes. Sorry for being a bit dense.
Oh, that's no problem. You should see me trying to use Teams.
I'm good at SQL Server, and that's where it stops.